We are studying nucleophilic addition reactions at aldehydes and ketones. We have already discussed strong nucleophiles attacking on aldehydes and ketones when we have, for example, hydrogen nucleophiles or hydrate, better yet, nucleophiles. Here we study the reaction with lithium aluminum hydride and sodium boron hydride. And then we also study carbon nucleophiles. Also, we have here in this very strong nucleophiles, we have Grignard, we have cyano here, and we have Wittig. So we study all those reactions. If you can go to those videos if you want to study any of those particularly. Now we're going to be discussing other nucleophiles. The strong nucleophiles that we have here, by the way, particularly this, the mechanism will be the typical mechanism under basic condition, which is if I have this ketone and I have a strong nucleophile, the mechanism under basic condition goes by nucleophilic attack first. And then we have proton transfer step. For example, in Grignard, we had added something here, and we have an alkoxide, and then we need a protonase. So typically, that mechanism is nucleophilic attack, proton transfer. Now we're going to be studying other types of nucleophile over to aldehydes and ketones. So let's draw aldehyde, and that's R. And ketones, we will have R prime, let's say. Always the idea is knowing these reactions and understanding the mechanism to be able to predict products when we're giving reactant in reaction conditions, or maybe given reactant and products, decide what is the best reagent to accomplish that and plan a synthesis. Okay. So other nucleophiles that can act over aldehydes and ketones are oxygen nucleophiles. And here we have in this category, we have, for example, we can have water, we can have alcohols, but we can also have OH. We can also have alkoxides. And these two are stronger bases, strong nucleophile. Other nucleophiles that we will study later are sulfur nucleophiles. And similar to this, you will have the hydrogen sulfide or thiol or mercaptan. We also have here in this category diols, for example, this, or dithiols. So all of those. So we're going to be studying this reaction. So let's do the first reaction that we're going to be looking at is a hydration reaction in a couple of conditions. The hydration reaction, you're adding across the double bond of an aldehyde and a ketone, an H and an OH. We're going to see how that happens. See that we have here the following ketone. Under basic conditions, hydration can happen by the nucleophilic attack of hydroxide. So here you have, I'm going to make this an aldehyde better. So this is acetaldehyde. Reason for that is that aldehydes are more reactive than ketones. And in the equilibrium, the hydrate, there is more aldehyde for the aldehydes, more content. So here, when you have basic condition, the first step is always nucleophilic attack. So here the products will be, I'm going to do it a different color. So you will have an alkoxide. Now you added OH here and you have an H. So you added here OH, and in the next step, we need a proton transfer. And to protonate that, and now you have this compound that has two OHs is the hydrate. This is the mechanism under basic conditions. Always under basic conditions, the nucleophilic attack is the first step, then proton transfer. Okay, now the hydration in glycerol and aldehyde can also happen under acidic condition. And if you have, notice under basic condition, you have the major species will be, say, water and hydroxide as your solvent, say. So we don't have, we need to pay attention with that to when we are proposing a mechanism. That is, in that step, hydroxide is better nucleophile, of course, than water. That's your nucleophilic attack. Now, under acidic conditions, what you have now, the major species, you have hydronium and its conjugate base, water. So here, the species that is nucleophilic is water, which is weaker nucleophile, of course, than OH. But again, this is what you have under those conditions. So the nucleophile will be water. And so now we're drawing this same aldehyde. Now, if we have typically the mechanism under acidic conditions involves proton transfer first. Reason being is this, for example, is weaker nucleophile. But if we do a proton transfer first, that is hydronium. If we do that, impregnate the oxygen. Now, this species, a carbon here, is more electrophilic than it was at the beginning. Because now, remember that you can do a resonance structure over here. And so in doing so, you're making, by protonating that oxygen, you're making this carbon more electrophilic. Now the nucleophile can attack better, even a weaker nucleophile. So now we have the nucleophilic attack by water. So what we need to see here is that the mechanism under acidic condition is proton transfer first, then nucleophilic attack. At the end, and I'm going to have to erase something here, which is what we did under basic condition. I'm going to erase that. So that to continue this reaction. Now we said this is basic conditions, so nucleophilic attack. Proton transfer is the second step. I'm going to draw this proton transfer, which, and that's my hydrate. Under acidic conditions, after you do, these are resonance structures. After you do the nucleophilic attack, here, let's draw what we form. We will have OH. I'm going to draw H. And now I'm going to have O, water. You will have an extra proton, notice. This is, you had the attack by water. So here you need an extra step to deprotonate that oxygen. And because under acidic conditions you have hydronium and water, the base that is going to remove that extra hydrogen is water. And in doing so, here electrons back to the oxygen, you forming the hydrate. So under acidic condition, we have one step more. First step was a proton transfer here, nucleophilic attack, this time by water, and then another proton transfer. Under basic conditions, we only had 2 steps. And remembering the mechanism help us predict products. So bottom line, you're doing a hydrate. A hydrate has 2 OHs, and you can do it under basic or under acidic condition. So when you see a carbonyl compound under here reacting with OH or hydronium, one thing that can form is a hydrate, but the hydrate forms this in large extent for small aldehydes, such as methanol or formaldehyde. Not very much so if larger compounds, particularly. Always it's better for aldehydes than ketones, but smaller aldehydes.